So, welcome. How's everybody? Good. Good. So my goals for today are to answer any questions that you have, and then talk about Chapter 3 content for a while, and then I have a review assignment for the exam. So, Brian had a question about the graphs, and that's good, because those will be on the exam. Before we get to the graphs, do you have any other questions? Been using the study guide? Make sure you bring your calculator and pencil. You may also want to bring a piece of scratch paper. The exam has lots of room to write, but you may want a little bit more room. So make sure to come prepared. If there's no questions, let's go ahead and get into these graphs. And so these graphs at the end of Chapter 2 go over kinematic variables. And when we talk about kinematic variables, we're talking about position, which we define as displacement when we have a change in position. And then when we talk about the rate of change in position, we define that as velocity. And then the rate of change in velocity is defined as acceleration. So those three things, displacement, velocity, and acceleration. So if we were to track the center of mass of an individual as they perform either a squat jump or a counter movement jump, we would come up with graphs that look like this. So in our lab, we perform both types of jumps. So the basic difference is that a squat jump, we don't have a loading phase. And so when I say loading phase, that means a pre-stretch or a preparatory phase where the jumping muscles undergo a rapid change in length. And so the muscles store this elastic potential energy, and we stimulate the stretch reflex, and we get this huge force output on the concentric part. And so with a counter movement jump, because of the stretch reflex and because of elasticity, we jump higher, or we should jump higher. Whereas with a squat jump, it's only a concentric type action. It's just an upward push from the ground. So there's no stretch reflex or elasticity contribution to that. So as we track a person's center of mass, and how do we define center of mass? The COM, center of mass, or sometimes COG, center of gravity. What's the definition? Yes, yeah. So it's the point around which the mass of a body is equally balanced and distributed. Does that point change, or can it change? Yeah, so as we shift our center of mass, or the segments of our body, as we position our body segments in different ways, the center of mass shifts according to where the mass has the greatest concentration. And so with these graphs, for me at least, it's easiest to visualize the position graph. So this one up here for counter movement jump and for squat jump. You can kind of see the movement of the center of mass as you go through the load phase. Okay, so this would be the quick squat prior to the jump. Your center of mass would drop, and it's easy to visualize that. Hey, Logan. And then eventually, the preparatory phase comes to an end. So you have that quick squat, you reach the bottom of that squat, and then you begin to come up into your jump. And so we can see the center of mass as it rises, and the 0 point here would be when the feet leave the ground. So at that point, the body has become a projectile. So projectile motion. What is the vertical acceleration of a projectile through its entire path of flight? Vertical acceleration. Yes, that's number, I promise you, we will never stop using that number. It comes up over and over again all through the semester. So vertical acceleration. So a body or object will slow down in the positive direction until it reaches the peak of its flight. Okay, so we can see the center of mass rises until we have a peak in jump height, and then the center of mass gradually drops. So speeding up in the negative direction. So the vertical acceleration of a projectile going up and coming back down is negative 9.81 meters per second squared in both cases. How does the time up compare with the time down? The time up is equal to time down, is right. So just a few questions for you. Is everybody clear on the point at which the feet leave the ground? That's the 0 mark right here. So these graphs line up so that each phase of the position or displacement matches velocity and matches acceleration. So the center of mass gradually rises and then gradually falls. So another question for you. Can you identify the point where the counter movement ended on the velocity graph? Can you identify the point where the counter movement ended just before the jump began? Would someone be brave enough to come up and park? Yeah. So when the counter movement comes to an end, that means your body is coming to a stop just before you begin to rise. So what would your velocity be when the counter movement ends? It'd have to be 0. So we're talking about that point, right? I can get it. Right there is where the counter, welcome Maisie, that's where the counter movement comes to an end. 0. The counter movement comes to an end and then you're pushing in the positive direction. Okay. Let me ask you another question. Can you identify the point on the velocity graph where the center of mass was at its peak height? Can you identify the point on the velocity graph where the center of mass was at the peak height? So in other words, they were at the peak of their jump in height. What do you think?
Wouldn't that be the next time it crosses the horizontal line?
Yeah, very good. So that would be right there. Now everybody, other than Joe, everybody take a look. Tell me why that would make sense on the velocity graph where the center of mass reached its peak height. Jump height was at its peak. Why would that correspond to this point on the velocity graph?
Velocity is 0.
Yes, that's exactly right. Velocity is 0. You're not going up anymore. So your velocity, when you jump, from a velocity standpoint, you're moving in the positive direction, certainly, as shown right here, but your velocity is decreasing towards 0 until you reach the peak of your jump. So velocity for the first half of the jump is decreasing towards 0 until you reach the peak height of your jump. And then once you reach the peak height of your jump, what happens to velocity on the way back down? You're increasing velocity, but in What direction? Negative. So velocity is a vector. So not only how much velocity, but in what direction. So velocity is increasing in the negative direction. And so you can see based on time that the segment from here to here and then here to here is equal. So we're spending an equal amount of time slowing down in the positive direction as we are speeding up in the negative direction. Does that make sense? Okay, all right, so, okay, so can you mark the first point after landing? So after landing, so now the feet have hit the ground. The first point after landing at which the body came to a complete stop for both jumps. The complete stop should give it away on the velocity graph. So if it's a complete stop, what's your velocity going to be? 0, yeah. So after, in the landing phase, the feet hit the ground right here, and then we are stopped right there. So body comes to a complete stop after landing. Okay, a couple questions on the acceleration graph. How does acceleration compare with force? We're going to be talking about this today when we cover chapter 3 on Newton's laws. How does acceleration compare with force? Yes, they are proportional. So Newton's second law tells us that the net force applied to or applied by a body or object is proportional to the mass multiplied by the acceleration. So if mass is constant, then as net force increases, we have an increase in acceleration that's proportional. So the more force you apply, and for athletes, often it's the ground that you're pushing against. The more force that you push into the ground with, how does that affect your acceleration? It increases it, right? So you go from a static position into motion with an increase in velocity that is proportional to the force you apply to the ground. So that, in summary, is the reason why we lift weights, right? Is that equation. So if we can keep our body mass consistent but become as strong as possible, think about that equation. The net force is equal to the mass times acceleration. So if we keep our body mass constant and become as strong as possible, we improve our capacity to produce force. That immediately improves our capacity to accelerate. So we more than absolute strength, we want athletes to be as strong as possible in a pound for pound sense. Does that make sense? Relative strength. Strength per pound of body weight is what we want more than absolute levels of strength. Because of the relationship between force and acceleration. So, getting back to this, if acceleration is proportional to force, where would the body be undergoing the highest amount of force? So you can, maybe it's too obvious a question, but it would be right here. What's going on right there? Based on the other graphs which match up, that's when you hit the ground. That's the impact. So do you notice that the body absorbs more force during the impact than put into the ground during the takeoff? And it's true that more often athletes will incur an injury during the landing phase of a jump versus the takeoff phase. So the landing phase is where our bodies absorb the greatest impact force. It's because gravity accelerates our body. So the higher we jump, the greater the velocity that we have going into the ground. So force and acceleration are mirror images of each other. So a higher acceleration means the body is absorbing or applying higher force. Okay, so can you tell me on the acceleration graph the part where the body was not in contact with the ground? You have an idea what part of this acceleration graph the body was not in contact with the ground?
So as it crosses the vertical axis and is flatlined at
Yeah,
-9.81.
the flat part, yeah. So right here, -9.81 meters per second squared. The body's not in contact with the ground, it becomes a projectile. So vertical acceleration during the entire flight phase, which it looks like was just under 0.6 seconds. -9.81 meters per second squared. Okay, can you tell me based on the acceleration graph where the counter movement came to an end? So when the counter movement comes to an end, what's your velocity going to be? 0. The counter movement comes to an end, you're not moving, so what's acceleration going to be? 0. So it's going to be right there. Okay. All right, so before we move on, are there any questions? Is everybody pretty clear on position, velocity, acceleration, comfortable?
Maybe this is too far in the weeds, but on the velocity chart, once the body comes to a complete stop, you have that last hump.
Last hump. Okay, so your body comes to a complete stop. So you jump, complete stop.
And then you stand.
Am I fully standing up yet?
Okay.
This is when you're back to your baseline
Okay.
position. Any other questions?
Can you just explain again, why is it the highest center of mass on the velocity graph?
Yes. So this shows you your vertical velocity. So up and down velocity. So this would be when your center of mass reaches the peak height. So your center of mass goes up until you get to the top of your jump, and then you come back down. So that's all jumping is. You're either going up or coming down. There's no in the middle phase. So the time that you're going up is equal to the time coming down if we ignore air resistance, which in most cases we can. So at this point, when your body's no longer going up, and for that instant in time, when you're not going down either, what would your velocity be? Yes, you're not going up anymore, and just before you start to come down, that brief instant, your velocity is going to be 0 right here.
Oh, okay.
So 0 velocity. So you can see that our velocity is decreasing on the way up, and then our velocity is increasing on the way down. Any other questions? Okay, all right, so I want to make sure we get to the review assignment, so let's briefly get into chapter 3. And we'll get in some groups and do some review. So chapter 3, kinetics, different than kinematics. Kinematics describes is the description of motion. displacement, velocity, acceleration. Kinetics considers the force. The force is that cause motion, that cause a change in position or a change in velocity or acceleration. So kinetics means force. So we have 3 laws that explain how forces can affect motion. So the first law is called the law of inertia. What does inertia mean? Yeah, so it's the reason you wear a seatbelt, right? So if you don't have a seatbelt on and you get in a crash, your car stops, but your body doesn't unless you have a seatbelt on. So inertia is defined as a resistance to change in motion. So in other words, a body at rest will tend to remain at rest unless what? Acted on by a net external force. So there has to be a net force, because a body can be at rest and have multiple forces acting, but if all those forces are balanced, then there won't be a change in the state of motion. So the law of inertia says an object will remain at rest, or if an object was moving to begin with, will continue moving at a constant velocity unless acted upon by a net external force. So there has to be an imbalance in forces for a body or object to change its state of motion. Newton's second law is sometimes called the law of acceleration. So we talked about this one today. So the amount of acceleration or change in velocity undergone by a body or object is proportional to the net force. So the greater the net force, the greater the change in velocity, or the greater the acceleration will be. So Newton's second law shows us that when we have a net force, when forces are not balanced, the amount of imbalance, or the net force, will be proportional to the acceleration. So then we get to Newton's third law, the law of action and reaction. So this law says for every force, there's an equal and opposite reactive force. So in chapter 1, we solved for the reactive force. You remember the truck pull example? So we looked at all the vertical components of this person pulling an 8-ton truck. And one of the overall vertical component we solved for was the ground reaction force. So the ground reaction force has a vertical component that's called the normal contact force, and also can have a horizontal component, which we call friction. So the reactive force from the ground can have both vertical and horizontal components depending on how we're pushing into the ground. So Newton's 3 laws of motion. We study those laws to determine how forces affect the motion of a body or object. So the first law, just some simple examples. So if there's 0 net force, all the forces are in balance, what will acceleration be? Yeah, so with Newton's first law, there's 0 acceleration. So it's sometimes confusing because Newton's first law can apply to a body that's moving along at a constant velocity. So it's moving, but if the movement is constant, then there's 0 acceleration. So all the forces are in balance. So there has to be a net unless acted on by an unbalanced force. There has to be a net force to change the motion of a body or object. Okay, so what about projectile motion, and how does that apply? Well, if we ignore air resistance, What's the horizontal acceleration of a projectile? So if I was to throw a ball and that ball had both vertical and horizontal components, you know what the vertical acceleration is. Talked about it, negative 9.81 meters per second squared. If we ignore air resistance, what's the horizontal acceleration of a projectile? It'd have to be 0. Yeah. We don't get to air resistance until chapter 8. But for now, if we ignore air resistance, then the horizontal acceleration is 0 because the body or object will continue moving along horizontally at the same velocity until gravity brings that object down to the ground. Okay, so other practical examples where all the forces are in balance. I like to think of, as I was preparing this chapter, think of static exercises. How many of you have done static exercises? I better see all the hands go up. We should do this one.
Which one? Oh, I've done that. That's
You've done that. I get to be the one that walks across the top.
That's punishment.
So not the one that's walking across the top, but the other guys underneath. That's static. So all the forces are in balance. Okay, done hundreds of planks, right? That's static. So we're not moving. All of our torso muscles, so sometimes called the core muscles, the spinal stabilizers are tensed. So our motion doesn't change. We're in a state of equilibrium. Okay, here's a good one that sometimes Logan does, throwing athletes do. So we're in a state of static equilibrium. Has anyone tried this? Pretty tough with that ball kettlebell there.
Watched you grab the biggest
A lot of
kettlebell and do it
restraint.
in a sweat.
What?
I watched you grab the biggest
Me.
kettlebell and do it in a sweat.
No extra credit. All right. So weight equals reactive force. Weight equals reactive force. So the weight, which is equal to what? What is weight equal to? What do you say if you don't know? Gravity, correct. Is equal to the reactive force from our hand. So weight acts down through our hand, and the hand applies a reactive force to the weight. So if the weight's not moving, okay, then everything's in equilibrium. So Newton's first law would apply. There's no change in motion. So if we go from this case where we're holding a weight, what do we have to do to get that weight to move? The reactive force has to be greater than what? The weight, to cause a change in motion. So that initial push would be determined by the net force. What's the reactive force, and how does that compare with the weight? The greater the force from our muscles, the greater the change in velocity. The faster that weight will go up with a greater reactive force from our muscles. So weightlifting, competitive weightlifting, applies a lot to this scenario where you have this massive amount of weight on the ground. What are the two lifts that are contested in Olympic weightlifting? Yes, the snatch and the clean and jerk are the two official lifts. And so you have this big weight on the ground, and you have to bring that weight in a fraction of a second from the ground over your head in the snatch. So the weight on the ground is at rest, and you have to apply a tremendous reactive force to get that weight to accelerate to a position where it comes to rest over your head. It takes a lot of skill and practice. So lots of athletes for weeks will practice just with PVC pipes. How many have seen those that you practice with to get the motion before you transition into a loaded barbell? It also requires a tremendous amount of mobility in your hips and your ankles. You have to be comfortable holding a heavy weight over your head, but in a full squat position. So the heavier that weight, the lower you're going to be when you catch it. So it takes a tremendous amount of strength and athleticism, which is why athletes use a lot of the Olympic weightlifting movements and variations, because there's such a benefit for lots of different athletes in doing these types of lifts. Okay, so interpretations of Newton's first law, it just all comes back to forces being in balance. So you can read through these as I put them up. So anytime we have zero net force, zero acceleration, we're going to have an object that's not going to change its state of motion. It's going to keep moving or remain at rest. Applications of Newton's first law. Let's talk about collisions. Do collisions ever happen in sports? You can tune in this weekend and see some. So, conservation of momentum principle. Okay, so if we consider the two objects or bodies in a collision as a system, then the momentum, the combined momentum of each object before the collision will be the same as the combined momentum of the objects after the collision. So if something is constant, in this case, the total momentum before the collision and after the collision, we can see that constancy is what applies to Newton's first law. Constancy of momentum. So linear momentum has two components. There's a mass component and a velocity component. So you think about momentum in the context of football. We want football players to be large and fast. So football places a premium on large, fast players because they generate more momentum. So they're more difficult to move, and once they're moving, they tend to keep moving. They're harder to stop. So if the velocity of an object is constant, then its momentum is constant as well, because mass doesn't change. So if we look at two objects like two football players before a collision versus after a collision, and in a hypothetical scenario, if the momentum of both players combined before the collision is the same as both players after the collision, momentum is conserved, and so we can say the net force is equal to 0. So let's consider a couple of different types of collisions: elastic versus inelastic. Elastic versus inelastic. So in perfectly elastic collisions, the objects or bodies will separate following the collision. Okay, so oftentimes elastic collisions are described with one object colliding with an immovable object. Like if I held a basketball up at a height of 6 feet and I dropped the ball, it's going to accelerate towards the ground, and if the ball has the right amount of pressure in it, it's going to bounce. Okay, but does the ball bounce to the same height that I dropped it? No, it doesn't. So there's a little bit of momentum lost in that collision with the ground, right? So if momentum was completely conserved, then if I dropped a ball from a height of 6 feet, it would hit the floor and it would bounce to the same height that I dropped it from. Okay, so we can say that there's some momentum, or we could say mechanical energy, that is lost as the ball collides with the ground. So we can look at collisions on a spectrum. We can look at collisions where there's 100% conservation of momentum, where there's no loss of energy or momentum prior to and after the collision. Think of the ball, it bounces to the same height that I dropped it. That's a perfectly elastic collision. On the other hand, we have perfectly inelastic collisions. Inelastic collisions, the objects or bodies stay together following the collision. So there's a 100% loss of momentum following the collision. So let me tell you a little story. So my wife and I first got married. We lived in Arizona and I was attending Arizona State, and I got almost to the very end of my doctorate program, and then we had our first daughter, Vanessa, and she's graduating from high school this spring, so years go by fast. But we were poor, and we could afford to have one good meal a week. So we would look forward to this meal all week long. We were on a very small budget. And so we made homemade pizza. How many have done that? Made homemade pizza, it's the best. And so I was holding Vanessa, and she was looking at this pizza, and she reached out her foot to the counter, and she just got one toe on that pizza, and she pulled it off the counter. Did the pizza bounce? No, it didn't. That was a perfectly inelastic collision. So the loss of the good meal for the week. So in an inelastic collision, momentum is lost into the ground as a result of the collision. Okay. So most collisions in American football are somewhere on this continuum between perfectly elastic and perfectly inelastic. They're somewhere in the middle. So there's some energy that is lost due to pads, which is a good thing, right? Because we want collisions to be less elastic in football. That's what the purpose of pads is to absorb all of that energy and lose some of that momentum during this collision. Okay. So what I want to do is take this hypothetical scenario. So in this case, let's assume that in this collision we have 100% conservation of momentum from before to after the collision. So if we consider two athletes as a system, and so the total momentum of the system is constant before to after, we can solve for the outcome. In other words, what is the velocity following the collision? So I want you to consider the two players together, and we're going to add up the total momentum of the players before the collision, and then we're going to compare that with the total momentum of the players moving together after they collide. So hypothetically, we're going to say that the momentum is conserved from before to after. And again, it's in reality, there's a loss of momentum due to pads that absorb the impact, but just for the sake of example. So an 80-kilogram running back collides in midair with a 120-kilogram linebacker. Okay. at the goal line during a goal line stand. Just before the collision, the running back had a velocity of 6 meters per second. So two things that we need to know to get momentum. We need mass and we need velocity. So let's define the velocity of the running back as positive. So towards the goal line is positive velocity. So we'll say this is a positive 6. So you're going to, let's begin here. So you're going to say mass of 80 kilograms. Okay, so that's, we'll say number 1 is the running back. So mass of 80 multiplied by a pre-collision velocity. So that's denoted with a U, pre-collision velocity of positive 6 meters per second. So 80 times 6. So you multiply that together, what'd you get? 480 kilogram meters per second is momentum. Plus, okay, so 120 kilograms, okay, towards the goal line. The linebacker had a velocity of 5 meters per second in the opposite direction. So that 5 meters per second is in the opposite direction, so it's negative. So 120 multiplied by negative 5 is what? Yeah, 600 kilogram meters per second. So you put those two together, you add 480 kilogram meters per second, and you subtract 600 kilogram meters per second. So what is the total momentum of that system, considering two players together prior to the collision? What do you have prior to the collision as the total momentum of that system? Yeah, negative 120 kilogram meters per second. Does everybody understand how we got, Jackie, do you understand how we got that? Okay. Okay, so 480 minus 600, we get negative 120 kilogram meters per second. Okay, so what we're doing is assuming that after the collision, the momentum is constant, for the sake of example. So after the collision, okay, if the collision was perfectly inelastic, momentum is 100% conserved, would the running back be moving forward and score a touchdown just after the collision, or would the defense prevail? So what we're saying is after the collision, after they collide, they're moving together as one mass. So mass 1 is 80, mass 2 is 120. So what's the total mass? 200 kilograms. And then you have the post-collision velocity. So can you solve for the post-collision velocity? So you take 200 kilograms, divide by 200 on each side of the equation. What did you come up with for a post-collision velocity? Yep. So in this case, the defense prevailed. So the linebacker is able to move the running back in that opposite direction of motion. Okay. So I want to give you just a little bit of time here. Yeah, we're good. So to work on some review. The exam is going to consist of concepts and then things where you'll have to do math. So you'll be given all of the equations. It's just a matter of knowing how to put those variables in the equations. So for the concepts part, what I have is just a review I'd like you to do in groups. This is worth 10 points. Work together think carefully about your answers. This will be very similar to the types of conceptual questions you'll see on the exam. Oh,
So sorry.
you can work however you'd like.
Jeff will be given equations.
Yeah, don't spend time memorizing equations. So let's do the first one together. What's the difference between mass and weight? How do we define mass? How would you define mass? So the quantity of matter that comprises a body or object. So mass is independent of gravity. Quantity of matter. So weight is equal to the force of gravity acting on a body's mass. Which one of those quantities is a vector, mass or weight? Weight is a vector, which means magnitude and direction. Mass is, what's the other type of quantity? Vector, and then what's the other one? Scalar. Yes, would be no direction. How do we calculate gravitational force? In other words, how do we calculate weight? Yes, mass times negative 9.81 meters per second squared.